You know that app you use to order coffee? Or the operating system running on your computer right now? Well, there's a really powerful design philosophy working behind the scenes for pretty much all of it. It's called Object-Oriented Programming, or OOP. And today, we're going to pull back the curtain and see exactly how it works.
I mean, just stop and think for a second about how complex modern software is. We're talking millions of lines of code. So how on earth do developers manage all of that without it turning into a complete, tangled mess? Well, the answer is they've learned to think about code not as one giant long list of instructions, but as a collection of smart, self-contained blueprints.
And here's our roadmap for today. We're going to start with the absolute core idea, the difference between a blueprint and an actual object. Then, we'll dive into the 4 foundational pillars that give this whole approach its power: encapsulation, inheritance, polymorphism, and abstraction.
Okay, first things first. Before we go anywhere else, we have to understand the absolute heart of OOP. And it really all comes down to just 2 concepts: the plan and the thing you build from that plan. Think about it. Before you build a house, you need a blueprint, right? Before you build a car, you need a design schematic. It's the exact same idea in programming. This blueprint, this template, is what we call a class. As you can see in this little code snippet, we're not building a car, we're defining the idea of a car.
Now, this is the crucial part to get. A class isn't the car itself, it's the concept of a car. It just outlines what any car should have, like you see here, properties for color and speed, and what it should do, like a function to start. It's the master plan. Okay, so this is where the magic happens. We take that car blueprint and we actually create a specific car from it. In this code, you can see we're creating a real thing called my car, and we're giving it a specific color, red. We're taking that general idea and making it a concrete reality.
And that's what an object is. It's a real, tangible instance that was created using the class blueprint. So if the class is the recipe for a cookie, the object is the actual delicious cookie you can hold and eat. And you can use that one recipe to make dozens of different cookies.
So let's just put them side by side to make it absolutely crystal clear. The class, that's the blueprint, the design for a car in general. The object, that's my specific red car sitting in the driveway. The class is the concept. The object is the reality. You have to get this distinction because it is the bedrock of everything else we're about to talk about.
So, if classes and objects are the materials, what are the rules of construction? That's where the 4 pillars of OOP come into play. And trust me, these aren't just buzzwords. These are the core principles that make this whole system so organized, efficient, and incredibly powerful.
You can almost think of these 4 pillars as superpowers for our code. We've got encapsulation, abstraction, inheritance, and polymorphism. Each one solves a very specific kind of problem, and together, they help programmers build software that's reliable and can grow without collapsing. So let's break them down one by one.
Our first pillar is encapsulation, and really this is all about keeping things neat and tidy by bundling related things together into a nice self-contained package. At its core, what encapsulation really means is that a class, our blueprint, should package up all of its own data and the tools that work on that data. So a car's speed and the function to change that speed, they should live together right inside the car object. They're one single unit. An ATM is the perfect real-world example of this. You interact with a super simple screen and a keypad. You have no idea about all the complex machinery and logic happening inside. All that complexity is encapsulated. It's hidden away, which both protects it from you messing with it and, more importantly, makes the machine incredibly simple for you to use.
Okay, let's move on to our second pillar, which really builds on that first idea. This one is all about efficiency and not having to reinvent the wheel. It's called inheritance.
Inheritance is, well, it's pretty much exactly what it sounds like. It lets us create a new class that's basically a more specific version of a class that already exists. This new child class automatically gets all the features of the parent class, so we don't have to write all of that code over and over again.
It's just like a child inheriting traits like eye color from their parents. A car class can inherit basic properties, like has wheels, from a more general vehicle class. Then, the car class only needs to add the stuff that's unique to it, like, say, a sunroof. This is so powerful, and it helps keep code DRY, which stands for Don't Repeat Yourself.
All right, pillar number 3. Now this one has a kind of complicated sounding name, but I promise you the idea behind it is actually super intuitive. Polymorphism. It literally just means many forms. The core idea here is that we can have a single action or command that does totally different things depending on the situation. So imagine you tell a bunch of different animals to speak. Well, a dog object will bark, a cat object will meow, and a cow object will moo. The command is the same, but the result is totally different for each object.
Here's a great example from real life. The same person acts differently depending on their role, right? They're one way as a teacher, another as a customer, and another as a parent. Or just think about the main button on your phone. In a call, it hangs up. In a messaging app, it sends. One button, many forms, different behaviors based on the context. That's polymorphism.
And that brings us to our final pillar, abstraction. Now, if encapsulation is all about hiding complexity inside an object, abstraction is about hiding that complexity from the person using the object. Abstraction is all about making things simple. It means we only show the user the essential features they need to interact with, and we hide all the unnecessary, complicated stuff under the hood. It's about creating a simple interface for a very complex system. You use this concept every single day. You don't need to be a mechanic to drive a car, right? The insane complexity of the engine is abstracted away, leaving you with just a simple steering wheel and a couple of pedals. Same thing with a TV remote. You press the power button, the TV turns on. You don't need to know anything about infrared signals or circuitry. That's abstraction in action. So let's just pull it all together one last time. Encapsulation bundles everything up neatly, like an ATM. Inheritance lets us reuse code, like a child inheriting traits from a parent. Polymorphism lets one name have many forms, like a person in different roles. And abstraction hides all the messy details, like the engine of a car. These four pillars work together to create software that is organized, reusable, and so much easier to manage. So there you have it. From a simple blueprint and a single object to these four powerful principles of construction. This is the logic that underpins so much of our modern technology. It's a way of thinking that turns chaotic complexity into elegant, manageable design. So the only question left is, what will you build with it?